Let me tell you something that might surprise you. There was a time, thousands and thousands of years ago, when the number 3 didn't exist. Not that there weren't 3 of things. 3 stones, 3 stars, 3 children tugging at someone's arm. But the idea of 3, the pure concept of threeness, as something you could hold in your mind separately from the stones or the stars or the children, that idea hadn't been born yet. And the fact that it eventually was born, that human beings somehow pulled abstract numbers out of the raw fabric of everyday life, might be the most remarkable thing our species has ever done. More remarkable than fire. More remarkable than language, even. Because once you have numbers, once you have mathematics, you can describe the hidden architecture of absolutely everything. But tonight, we're not in any rush. We're going to walk through this slowly, starting from the very beginning, from a time before writing, before cities, before anyone had ever drawn a straight line on purpose. And we're going to follow this thread forward, through centuries and civilizations, watching how one insight leads to another, how problems that stumped the greatest minds for generations suddenly crack open because someone looks at them from just the right angle. Some of it is going to be strange. Some of it is going to be beautiful. And all of it, every bit of it, connects to the world you live in right now. The phone on your nightstand, the roof over your head, the way your bank calculates interest, the path a satellite takes around the earth. All of that is mathematics, and all of it started with someone, somewhere, a very long time ago, making a scratch on a bone. That's not a metaphor, by the way. One of the oldest mathematical artifacts we've ever found is a bone. It's called the Ishango bone, and it was discovered in 1960 by a Belgian geologist named Jean de Heinzelin near the headwaters of the Nile, in what is now the Democratic Republic of the Congo. It's a baboon fibula, just the leg bone of a baboon, and it's about 20,000 years old, maybe older, and carved into it are a series of notches grouped in very deliberate patterns. One column has groups of 11, 13, 17, and 19. Those are all prime numbers. Another column seems to show a doubling pattern. Now, whether the person who carved those marks actually understood prime numbers or doubling as concepts, that's genuinely debated. Some researchers think it's a lunar calendar. Others think it's a tally stick, a way of keeping count of something. Trades, days, kills. We honestly don't know for certain. But here's what we do know. Someone, 20,000 years ago, was organizing quantity. They were grouping. They were keeping track. And that impulse, the impulse to impose structure on the raw flow of experience, that's where mathematics begins. Think about what life was like before counting. You'd have what cognitive scientists sometimes call a sense of numerosity, this fuzzy, instinctive feeling for amounts. You can see it in animals today. A crow can tell the difference between 2 pieces of food and 3 pieces of food. A lioness can assess whether her group outnumbers the rival group across the river, but it's approximate. It's vague. It breaks down fast once the numbers get bigger. You can glance at 3 dots and instantly know there are 3. You can do the same with 4. But show someone 7 dots and 9 dots side by side, and suddenly you need to actually count. That transition, from feeling quantity to counting quantity, took our ancestors a staggeringly long time to make. Tens of thousands of years, probably. And the tool that made it possible was so simple, it's almost funny. It was the one-to-one correspondence. You match each sheep in your flock to a pebble in a pouch. One sheep, one pebble. Another sheep, Another pebble. You don't need a word for 17. You don't need to know what 17 means. You just need to know that when the sheep come home at night, every pebble should have a sheep. If there's a pebble left over, you're missing one. And that's exactly what people did. In fact, the Latin word for pebble is calculus. That's where we get the word calculate. Every time you hear someone talk about calculus, this supposedly terrifying branch of higher mathematics, just remember, it literally means playing with little stones, which is kind of wonderful, right? Now, let's move forward a few thousand years, because the really interesting stuff starts happening when people settle down. When you're a nomadic hunter-gatherer, your mathematical needs are pretty modest. You need to track seasons, maybe count members of your group, keep a rough sense of time. But the moment you start farming, everything changes. Suddenly, you need to measure land. You need to know how much grain you've stored. You need to predict when the river will flood. You need to divide a harvest among families, and you need to do it fairly, or someone's going to be very unhappy. Agriculture doesn't just need mathematics. It demands it. And the place where this demand first produced something truly extraordinary was Mesopotamia, the land between the Tigris and Euphrates rivers in modern-day Iraq. Around 5,000 years ago, the Sumerians developed one of the earliest writing systems, cuneiform, and they used it. Here's what's fascinating. They used it primarily for accounting. The earliest cuneiform tablets aren't poetry. They aren't myths. They're records of grain shipments, livestock counts, land measurements, beer rations. Mathematics came before literature. Think about that. The very first reason human beings felt compelled to write things down was to do math, to keep track of who owed what to whom. The Sumerians and, later, the Babylonians developed a number system that was base 60. We use base 10, probably because we have 10 fingers, but the Babylonians used 60 as their fundamental grouping unit. And before you think that's bizarre and arbitrary, consider this. You still use base 60 every single day. There are 60 seconds in a minute, 60 minutes in an hour, 360 degrees in a circle. That's all Babylonian. They gave us that, and it stuck for 4,000 years. The reason 60 worked so well is that it's extraordinarily divisible. You can divide 60 evenly by 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. That makes fractions much easier to work with. If you're dividing grain among different numbers of workers, base 60 gives you clean, simple portions far more often than base 10 does. It was a practical choice, born from the daily reality of managing a complex agricultural economy. But the Babylonians didn't stop at counting and measuring. By around 1800 BCE, they were doing things that would genuinely impress a modern algebra student. We know this because of clay tablets, thousands of them, preserved in the dry Iraqi soil for nearly 4 millennia. One of the most famous is called Plimpton, 322. It's a small clay tablet, about the size of your hand, covered in cuneiform numbers, arranged in rows and columns. And when mathematicians finally decoded it in the 20th century, they realized it contained a systematic list of Pythagorean triples, sets of whole numbers where the square of one equals the sum of the squares of the other two. You know, like 3, 4, 5, or 5, 12, 13. The relationship you probably learned in school as the Pythagorean theorem, a squared plus b squared equals c squared. The Babylonians knew about this relationship more than 1,000 years before Pythagoras was born. They didn't call it the Pythagorean theorem, obviously. They probably didn't even think of it as a theorem in the way we understand that word. But they knew the pattern, they used it, and they recorded it with a level of sophistication that suggests a deep, working understanding. And they weren't just playing with whole numbers either. The Babylonians could solve what we'd now call quadratic equations. Equations where the unknown quantity is squared. They had systematic procedures, step-by-step methods for finding solutions. Not formulas written in symbolic algebra, because that notation wouldn't be invented for another 3,000 years, but verbal recipes. Take the coefficient, halve it, square the half, add it to the number, take the square root. It reads almost like a cooking recipe, and it works perfectly. They were doing real, substantive mathematics, and they were doing it on clay, with a reed stylus, in a world without paper, without pencils, without any of the tools we take for granted. Meanwhile, something equally remarkable was happening along the Nile. Egyptian mathematics developed along a somewhat different path, driven by somewhat different needs. The annual flooding of the Nile was both a blessing and a logistical nightmare. Every year, the river would swell, covering the farmland with rich, fertile silt, which was wonderful for crops, but also completely erasing all the property boundaries. Every single year, the Egyptians had to resurvey the land, re-establish who owned which plot, recalculate the areas. They got very, very good at geometry. In fact, the word geometry literally means earth measurement. Geo, earth, metron, measurement. And that's exactly what it was. Practical earth measurement, born from the need to redraw the map every time the Nile receded. The most famous Egyptian mathematical text is the Rind Papyrus, written around 1650 BCE by a scribe named Ums, who noted that he was copying from an even older document, possibly dating back to around 1850 BCE. It's essentially a mathematics textbook. 84 problems covering arithmetic, fractions, geometry, and basic algebra. The Egyptians had a particularly interesting approach to fractions. They almost exclusively used what we call unit fractions, fractions with 1 in the numerator. So instead of writing 2/5, they'd express it as 1/3 plus 1/15. This seems cumbersome to us, but they had elaborate tables for decomposing any fraction into a sum of unit fractions, and they could work with remarkable efficiency using this system. It's a good reminder that there's never just one way to do mathematics. Different cultures find different paths to the same truths, and sometimes those paths reveal things about the underlying structure that the more obvious approach misses entirely. The Egyptians also had a surprisingly good approximation for the area of a circle. In problem 50 of the Rind Papyrus, Ames describes a method that's equivalent to using a value of about 3.16 for pi. The actual value of pi is 3.14159 and change, so the Egyptians were off by less than 1%. For practical purposes, figuring out how much grain fits in a circular granary, say, that's more than good enough. And they arrived at this value not through abstract reasoning, but through careful measurement and experimentation. They were empiricists, these early mathematicians. They tested, they measured, they refined. But here's where the story takes a turn that changes everything. Because up to this point, mathematics was fundamentally practical. It was a tool. You used it to count grain, measure land, track the stars, build monuments. It was incredibly useful, even sophisticated, but it was always in service of something else. And then, around the 6th century BCE, something happened on the rocky shores and islands of the Aegean Sea that would transform mathematics from a collection of useful techniques into something far stranger and more powerful. The Greeks came along, and they asked a question that, as far as we know, nobody had ever seriously asked before. Not just, does this work? But, why does this work? Can we prove it? Can we know for certain, beyond any doubt, that it must be true? And the person traditionally credited with sparking that revolution, though the real history is murkier and more complicated than the legend, was a man born on the island of Samos around 570 BCE. You've heard his name. Everyone has. But the real story of Pythagoras is far weirder than anything you learned in geometry class, and it starts with a journey, because before Pythagoras ever became the name you associate with right triangles and squared hypotenuses, he was a traveler, a seeker, and the things he went looking for and the places he found them shaped everything that came after. Pythagoras grew up on Samos, this lush green island just off the coast of what's now Turkey, and Samos in the 6th century BCE was not some backwater. It was a prosperous trading hub connected by sea routes to Egypt, to Phoenicia, to Babylon. The ancient world was more interconnected than we sometimes imagine. Ideas traveled along those trade routes just as surely as olive oil and purple dye. And according to ancient sources, and here I should say that almost everything we know about Pythagoras comes through later writers, some of them writing centuries after his death, so there's a lot of legend mixed in with whatever kernel of truth might be underneath. According to these sources, the young Pythagoras traveled. He went to Egypt, where he may have studied with priests for years, absorbing their mathematical knowledge, their geometry, their methods of calculation. Some accounts say he then went to Babylon, where he would have encountered that sophisticated base 60 arithmetic we talked about, those procedures for solving equations, those tables of numbers. Whether these specific journeys really happened, we can't say for certain. But the broader point is plausible and important. The Greeks didn't invent mathematics out of nothing. They inherited a vast body of practical knowledge from older civilizations and then did something radically new with it. What Pythagoras did when he eventually settled in Croton, a Greek colony in southern Italy, was strange by any standard. He founded what can only be described as a mathematical cult, and I don't use that word loosely. The Pythagoreans were a secretive community with strict rules about diet. They famously avoided beans, though nobody's entirely sure why. About behavior, about loyalty. They believed that numbers were not just useful tools, but the fundamental substance of reality itself. All is number, they supposedly declared. And think about what a radical claim that is. Not numbers help us describe reality, but numbers are reality. The universe, at its deepest level, is made of mathematical relationships. Now, that might sound mystical, and honestly, it was. The Pythagoreans were as much a religious brotherhood as a mathematical school. They believed in the transmigration of souls. They had elaborate rituals. They swore oaths of secrecy about their discoveries. But here's what's fascinating. Embedded within all that mysticism was some genuinely brilliant mathematics. And the most famous result associated with them is, of course, the theorem that bears Pythagoras' name. In a right triangle, the square of the hypotenuse equals the sum of the squares of the other two sides. A squared plus b squared equals c squared. Now, we already talked about how the Babylonians knew about Pythagorean triples more than 1,000 years earlier. That Plimpton 322 tablet with its columns of numbers, they clearly understood the relationship between the sides of right triangles. So what did Pythagoras actually contribute? And this is where the Greek Revolution really shows itself. The Babylonians knew that certain specific numbers worked: 3, 4, 5, 5, 12, 13. They had lists, they had procedures, but as far as we can tell, they never asked why it always works. They never proved it. The Pythagoreans, whether it was Pythagoras himself or members of his school, we really can't say, are credited with providing a proof, a logical argument that demonstrates with certainty that this relationship must hold for every right triangle, not just the ones you've happened to measure, every single one. An infinite number of triangles, all obeying the same rule. And you can know this without measuring any of them, just by reasoning about it. That shift from "we've checked a lot of cases and it seems to work" to "here's why it must always work," that's the revolution. That's the thing the Greeks gave mathematics that changed it forever. The concept of proof. And it's worth sitting with that for a moment, because it's genuinely profound. When you prove something mathematically, you're not making a really good guess. You're not saying, "this is probably true." You're constructing an argument so airtight that it would be a logical contradiction for the conclusion to be false. That kind of certainty doesn't exist anywhere else in human knowledge. Science doesn't give you that. Science gives you theories that are extremely well supported by evidence, but could in principle be overturned by new data. Mathematical proof is different. Once something is proved, it stays proved. The Pythagorean theorem was true in 500 BCE. It's true now, and it'll be true in 1 billion years. It was true before anyone discovered it. That's a strange and beautiful thing. But the Pythagoreans also stumbled onto something that shook their worldview to its core, and the story of that discovery is one of the most dramatic moments in the history of mathematics. See, the Pythagoreans believed that everything could be expressed as ratios of whole numbers. Every length, every proportion, every quantity in the universe. It was all, at bottom, whole numbers and their ratios. What we'd call rational numbers, fractions. And this wasn't just a mathematical preference. It was a philosophical and almost spiritual conviction. The harmony of the cosmos was built on these clean, whole number relationships. They'd even discovered that musical harmony worked this way. A string half as long produces a note an octave higher. A string 2/3 as long produces a perfect fifth. Beautiful, clean ratios everywhere. And then someone, tradition says it was a Pythagorean named Hippasus of Metapontum, considered the simplest possible case of the Pythagorean theorem, a right triangle where both short sides are 1 unit long. By the theorem, the hypotenuse would be the square root of 2. 1 squared plus 1 squared equals 2, so the hypotenuse squared is 2, so the hypotenuse is the square root of 2. Simple enough. But what is the square root of 2 as a fraction? What two whole numbers, when you divide one by the other, give you the square root of 2? And Hippasus proved, using the Greeks' own method of logical reasoning, that no such fraction exists. The square root of 2 cannot be expressed as a ratio of whole numbers. It's what we now call an irrational number, and the proof is actually elegant enough to describe. You assume the square root of 2 can be written as a fraction in lowest terms, say p over q, where p and q share no common factors. Then you square both sides, and you get 2 equals p squared over q squared, which means p squared equals 2 times q squared. That means p squared is even, which means p itself must be even, because the square of an odd number is always odd. So p is 2 times some other number, call it k. Substitute that back in, and you get 4k squared equals 2q squared, which simplifies to 2k squared equals q squared. But now q squared is even, which means q is even too. And that's a contradiction. You said p and q had no common factors. But you just showed they're both even, meaning they're both divisible by 2. The assumption must be false. The square root of 2 simply cannot be a fraction. Think about what that meant to the Pythagoreans. Their entire philosophy rested on the idea that whole numbers and their ratios were the fabric of existence. And here was a proof, an irrefutable, logical proof, using their own methods, that even the simplest geometric figure, a square with sides of length 1, has a diagonal whose length cannot be expressed in their system. The universe had numbers in it that weren't ratios. Their worldview had a hole in it that couldn't be patched. The legend says they were so disturbed by this discovery that they tried to suppress it. Some versions of the story claim that Hippasus revealed the secret to outsiders and was drowned at sea as punishment, thrown overboard by his fellow Pythagoreans, or struck down by the gods, depending on which ancient source you read. Whether any of that actually happened, we have no idea. The story might be entirely apocryphal, but the fact that such a dramatic legend grew up around a mathematical discovery tells you something about how earth-shaking it was. This wasn't just an abstract puzzle. It was a crisis, the first great crisis in the history of mathematics. And the Greeks' response to that crisis is telling. They didn't abandon mathematics. They didn't abandon proof. Instead, they adapted. They developed a more sophisticated understanding of number and magnitude. They learned to work with irrational quantities geometrically, even if they couldn't express them as fractions. And this pushed Greek mathematics in a particular direction, toward geometry rather than arithmetic as the foundation of rigorous reasoning. If numbers could be treacherous, if they could harbor these irrational monsters, then geometry felt safer. You could draw a line segment of length square root of 2. It was just the diagonal of a unit square. You could see it, construct it, reason about it. You just couldn't write it as a fraction. This geometric emphasis would dominate mathematical thinking for the next 2,000 years, and its greatest expression came from a man working in Alexandria, Egypt, around 300 BCE. His name was Euclid, and what he created was arguably the most influential textbook in human history. It's called The Elements, and here's the thing about it. Euclid probably didn't discover most of the mathematics in it. He was a compiler, an organizer, a systematizer of extraordinary genius. What he did was take the accumulated geometric knowledge of the Greek world, theorems proved by Pythagoras, by Hippocrates of Chios, by Eudoxus, by Theaetetus, by dozens of mathematicians whose names we've mostly lost, and he organized it all into a single, unified logical structure. And the architecture of that structure is breathtaking. Euclid starts with definitions. What is a point? What is a line? What is a circle? Then he states 5 postulates, basic assumptions so simple and self-evident that anyone would accept them. Things like, a straight line can be drawn between any 2 points, and all right angles are equal. From those 5 postulates and a handful of common notions, he proceeds to derive, step by careful logical step, 465 propositions spanning plane geometry, solid geometry, number theory, and the theory of proportions. Each proposition builds on the ones before it. Nothing is assumed that hasn't been proved or postulated. The whole thing is a cathedral of logic, and it held up for over 2,000 years. The Elements went through more editions than any book except the Bible. It was translated into Arabic, Latin, Hebrew, and eventually every major European language. Abraham Lincoln taught himself to reason by working through Euclid's propositions by firelight. Einstein encountered it as a boy and later called it a wonder. And that 5th postulate, the one about parallel lines, the one that says that if you have a line and a point not on that line, there's exactly one line through that point parallel to the original. That seemingly innocent assumption would eventually crack open one of the deepest questions in all of mathematics. Because here's what happened. For centuries, mathematicians looked at that fifth postulate and felt uneasy. Not because they thought it was wrong, but because it felt different from the other four. The first four postulates are short, crisp, almost obvious. You can draw a straight line between 2 points. You can extend a line indefinitely. You can draw a circle with any center and radius. All right angles are equal. Those feel like the kind of things you just nod at and move on. But the fifth one, the parallel postulate, is wordy, complicated, and feels more like something you should be able to prove from the other four rather than something you need to assume. And so, for roughly 2,000 years, some of the finest mathematical minds in history tried to do exactly that. They tried to prove the fifth postulate. They tried to show it was a logical consequence of the other four, that Euclid had been slightly redundant, that you didn't actually need to assume it, and every single one of them failed. Let that sit for a moment. 2,000 years of failure. Ptolemy tried it in the 2nd century. Proclus tried it in the 5th century. Islamic mathematicians like Omar Khayyam, yes, the same Omar Khayyam who wrote the Rubaiyat, that beautiful collection of poems, he was also a brilliant mathematician, and he spent serious effort trying to prove the parallel postulate around the 11th century. The Italian Jesuit Giovanni Saccheri published an entire book in 1733 called Euclid Freed of Every Flaw, in which he tried to prove the fifth postulate by assuming it was false and looking for a contradiction. And here's what's fascinating. Saccheri actually stumbled onto the beginnings of non-Euclidean geometry without realizing it. He derived a bunch of strange, unfamiliar results from his negation of the postulate, and instead of recognizing that he'd discovered a perfectly consistent alternative geometry, he declared the results repugnant to the nature of a straight line, and concluded that Euclid must have been right all along. He was standing at the door of one of the greatest mathematical discoveries in history, and he turned away because the results felt wrong to him. It took almost another century before anyone had the courage, or maybe the clarity, to walk through that door. And when they did, it happened almost simultaneously in 3 different places, which is one of those strange patterns you see again and again in the history of ideas. Around the 1820s and 1830s, 3 mathematicians independently realized the same extraordinary thing. Carl Friedrich Gauss, the great German mathematician, many people call him the greatest mathematician who ever lived. Gauss realized that consistent geometries could exist in which the parallel postulate didn't hold, but Gauss never published his findings. He was famously cautious about his reputation, and he worried that the philosophical implications were so radical that he'd be ridiculed. He wrote about it in private letters, used the phrase, "the howl of the Boeotians," to describe the outcry he expected, and kept it to himself. Meanwhile, a young Hungarian officer named János Bolyai, the son of a mathematician who had himself spent years fruitlessly trying to prove the fifth postulate, wrote to his father in 1823 with breathless excitement. "I have discovered such wonderful things," he wrote, "that I was amazed. Out of nothing, I have created a strange new universe." Bolyai had constructed a complete, self-consistent geometry in which through a given point, not on a line, you could draw infinitely many lines that never intersected the original. His father, Wolfgang Bolyai, who was an old friend of Gauss, sent the work to Gauss for his opinion, and Gauss's response was devastating. He wrote back saying he couldn't praise the work because doing so would mean praising himself. He'd already discovered the same things years earlier. János Bolyai was crushed. He suspected Gauss of trying to steal his priority, and he never published another major mathematical work. It's one of those heartbreaking stories where the human cost of a mathematical moment is just enormous. And then there was Nikolai Lobachevsky, a Russian mathematician working in Kazan, far from the major European mathematical centers, who published his version of Non-Euclidean geometry in 1829, actually slightly before Bolyai's work appeared in print. Lobachevsky called it imaginary geometry and later pangeometry, and he spent decades developing and defending it against widespread skepticism and even ridicule. Now here's why this matters so much, and not just for mathematicians. What Bolyai and Lobachevsky and Gauss had shown was something profound about the nature of mathematical truth itself. For over 2,000 years, Euclid's geometry wasn't just considered mathematically correct. It was considered the geometry of the actual universe, the way space really worked. And the parallel postulate wasn't just a mathematical assumption. It was thought to be a fact about physical reality. When you showed that you could deny it and still get a perfectly consistent system, you were saying something radical, that mathematics doesn't have to describe the world we see, that there could be multiple self-consistent mathematical universes, and the question of which one describes our physical universe is an empirical question, not a logical one. That's a huge philosophical shift, and it turned out to be prophetic because about 80 years later, when Einstein developed general relativity, he needed exactly the kind of non-Euclidean geometry that Bernhard Riemann had developed. Riemann being the mathematician who took things even further in 1854, showing that you could construct geometries of curved spaces with all sorts of different properties. In Einstein's general relativity, the geometry of spacetime is not Euclidean. Massive objects curve the fabric of space itself, and the parallel postulate doesn't hold near a star or a black hole. Light doesn't travel in straight lines through curved spacetime. So those strange, seemingly useless geometries that Bolyai and Lobachevsky explored turned out to describe the actual structure of the universe. Mathematics invented for its own sake, with no practical application in sight, became the language of modern physics. That happens more often than you'd think. But let's step back from that cliff edge for a moment and return to ancient Alexandria, because there's another figure from that era who deserves some time. Someone whose story is just as remarkable as Euclid's, but in a completely different way. His name was Archimedes, and he lived in Syracuse, on the island of Sicily, in the 3rd century BCE, roughly a generation after Euclid. And if Euclid was the great organizer, the architect of logical systems, Archimedes was the great problem solver, the one who got his hands dirty, who wanted to know how things actually worked. You've probably heard the bathtub story. Archimedes leaping out of his bath shouting, "Eureka!" after realizing he could measure the volume of an irregular object by the water it displaced. That story comes from Vitruvius, writing a couple of centuries later, and it may or may not be literally true, but it captures something real about Archimedes. He was someone who saw mathematics everywhere, in the physical world, in machines, in the behavior of fluids and levers and floating bodies. He proved that the area of a circle is equal to pi times the radius squared. He calculated that pi lies between 223/71 and 22/7, an astonishingly tight bound that he obtained by inscribing and circumscribing polygons with 96 sides inside and outside a circle and computing their perimeters. Think about that. 96-sided polygons computed by hand, with the arithmetic getting progressively more complex at each step. The patience and precision required is staggering. But here's what really sets Archimedes apart and what makes him feel almost modern. He developed a method for finding areas and volumes that was essentially a precursor to integral calculus, nearly 2,000 years before Newton and Leibniz. It's called the method of exhaustion, and the basic idea is beautiful. Say you want to find the area under a curve or the area of some complicated shape. You approximate it with shapes whose areas you already know: triangles, rectangles, polygons. And you make the approximation better and better by using more and more of these simpler shapes, smaller and smaller, until the error between your approximation and the true area can be made as small as you like. You're exhausting the space, filling it up with known quantities until there's essentially nothing left over. This is, conceptually, exactly what a definite integral does. Archimedes didn't have the notation, didn't have the formal concept of a limit, but he had the idea. And in a text called The Method, which was lost for centuries and only rediscovered in 1906 on a palimpsest, a parchment that had been scraped clean and overwritten with a prayer book. In that text, Archimedes describes something even more remarkable. He describes using infinitely thin slices to compute volumes, balancing them on an imaginary lever, using the law of the lever as a heuristic to guess the right answer before proving it rigorously. It's mechanical reasoning applied to pure mathematics, and it's breathtakingly original. And then there's the way he died. In 212 BCE, the Roman general Marcellus besieged Syracuse. Archimedes, who was by then an old man, had designed war machines to defend the city: catapults, cranes that could lift enemy ships out of the water, possibly even focused mirrors to set ships on fire, though that last one is debated. The siege lasted 2 years, and when the Romans finally broke through, Marcellus gave specific orders that Archimedes was not to be harmed. But according to the most famous version of the story, a Roman soldier found Archimedes drawing geometric figures in the sand, absorbed in a problem. The soldier ordered him to come along. Archimedes reportedly said, "Do not disturb my circles," and the soldier killed him. It's probably embellished, maybe even apocryphal, but it endures because it says something true about the kind of person Archimedes was. Someone so consumed by mathematical thought that the fall of a city was less important than the diagram in front of him. Now, Archimedes and Euclid represent two poles of Greek mathematics: the systematic and the inventive, the architectural and the physical. But there's a third strand of Greek mathematical thought that we should talk about, because it leads somewhere unexpected. And that's the work of Diophantus of Alexandria, who lived probably in the 3rd century CE, several centuries after Euclid and Archimedes, in the later period of Greek mathematics. Diophantus is sometimes called the father of algebra, which is a little misleading because algebra as we know it, with symbols and equations and systematic methods, really comes from the Islamic world several centuries later. But what Diophantus did was write a book called the Arithmetica, in which he posed and solved problems about finding whole numbers or rational numbers that satisfy certain conditions. Things like, find 3 numbers such that the product of any 2 of them plus the third is a perfect square. These are what we now call Diophantine equations, and they're still a major area of research in number theory today. Fermat's last theorem, one of the most famous problems in all of mathematics, was literally scribbled in the margin of a copy of Diophantus's Arithmetica. Fermat wrote that he had found a truly marvelous proof that the equation x to the n plus y to the n equals z to the n has no whole number solutions when n is greater than 2, but that the margin was too narrow to contain it. That was around 1637, and it took until 1995, over 350 years, before Andrew Wiles finally proved it, and the proof was over 100 pages long and used mathematics that wouldn't exist for centuries after Fermat. Most mathematicians suspect Fermat didn't actually have a valid proof, but the problem he posed, inspired by reading Diophantus, drove enormous amounts of mathematical development. So Greek mathematics gave us proof, gave us geometry, gave us the seeds of calculus, gave us number theory. But after the decline of the Roman Empire and the closing of the great schools in Athens and Alexandria, the center of mathematical gravity shifted. And it shifted east to the Islamic world, where something remarkable was about to happen. A synthesis of Greek, Indian, and Babylonian mathematical traditions that would produce tools and ideas we still use every single day. And at the heart of that synthesis was a man working in 9th century Baghdad, whose name you almost certainly know, even if you don't realize it, because his name gave us the word algorithm. Al-Khwarizmi, Muhammad ibn Musa al-Khwarizmi. He was a scholar at the House of Wisdom in Baghdad, which was this extraordinary institution established under the Abbasid caliphs in the early 9th century. And when I say extraordinary, I mean it. Imagine a place that combined the functions of a library, a university, a translation bureau, and a research institute, all rolled into one. The Caliph al-Ma'mun, who ruled from around 813 to 833, was genuinely passionate about knowledge. He sent emissaries across the known world to collect manuscripts, Greek, Persian, Indian, Babylonian, and brought them back to Baghdad to be translated into Arabic. The scale of this effort is hard to overstate. Works by Euclid, Archimedes, Ptolemy, Aristotle, Galen, all of them were carefully translated, studied, commented upon, and then built upon. This wasn't just preservation, though preservation alone would have been a monumental gift to human civilization. This was active, creative engagement with the ideas, and Al-Khwarizmi was right at the center of it. Around the year 820, he wrote a book whose title, when you translate it, is something like The Compendious Book on Calculation by Completion and Balancing. In Arabic, the key word in that title is algebra, which means restoration or completion. And that word, algebra, is where we get the word algebra. So think about that. One book, written in 9th century Baghdad, gave us both the word algorithm from the author's name and the word algebra from the book's title. That's an astonishing legacy for a single human being. Now, what was Al-Khwarizmi actually doing in this book? Here's the thing. He wasn't doing algebra the way you learned it in school, with x's and y's and equal signs. None of that notation existed yet. Everything was written out in words. If he wanted to say x squared plus 10, x equals 39, he would write something like a square and 10 roots equal 39 dirhams. Dirhams, like the currency, because he was often framing problems in terms of commerce and inheritance. But what he was doing, beneath the verbal surface, was systematic. He was classifying different types of equations, 6 types to be precise, and then providing step-by-step procedures for solving each one. Those 2 key operations in his title, algebra and al-muqabala, completion and balancing, are essentially what we'd now call moving a negative term to the other side of the equation and combining like terms. He was giving people a general method, a recipe that would work for any problem of a given type. And that's exactly what an algorithm is, a step-by-step procedure guaranteed to produce a correct result. His name became synonymous with the concept itself. What made Al-Khwarizmi's work so powerful was that it drew from multiple traditions simultaneously. The Greeks had geometry and proof. The Babylonians, as we talked about earlier, had those sophisticated procedures for solving quadratic-type problems on their clay tablets, going back over 1,000 years before Al-Khwarizmi. And then there was India. And this is where another crucial thread enters the story, because Indian mathematicians had developed something that would change everything: the decimal place value number system, including the concept of zero as a number. Let's talk about that for a second, because the invention of zero is one of those things that sounds almost trivially simple until you really think about what it means. Earlier number systems, Egyptian, Greek, Roman, they didn't have positional notation the way we use it. In Roman numerals, the symbol V always means 5, regardless of where it appears. But in our system, the digit 5 means 5 or 50 or 500, depending on its position. And for that to work, you need a placeholder. You need a way to say, there's nothing in this column. That's what zero does. Without it, you can't distinguish between 52 and 502 and 5002. The Babylonians, with their base 60 system, had actually developed a placeholder symbol for this purpose, but they didn't treat it as a number in its own right. Indian mathematicians did. Brahmagupta, working in the 7th century, laid out rules for arithmetic with zero. 0 plus a number is that number. 0 times any number is 0. He even wrestled with division by 0, which, as you might know, is still undefined in modern mathematics. He got some of it wrong, actually, suggesting that 0 divided by 0 equals 0, which doesn't hold up. But the fact that he was treating 0 as a mathematical object, something you could operate on, was revolutionary. The Indian system, the digits 1 through 9 plus 0, arranged in a place value notation, was elegant, compact, and incredibly efficient for calculation. Try multiplying two large numbers in Roman numerals sometime, and you'll immediately appreciate what the Indian system offered. Al-Khwarizmi recognized this. He wrote a second major work, now often called On the Calculation with Hindu Numerals, which introduced the Indian decimal system to the Arabic-speaking world. From there, it eventually traveled to Europe, which is why we call them Arabic numerals today, even though their origin is Indian. The more accurate term is Hindu-Arabic numerals, and they are, without exaggeration, one of the most important technologies in human history. Not a physical technology, an intellectual one. A technology of representation that made all subsequent mathematics, science, engineering, and commerce vastly easier. And Al-Khwarizmi wasn't working alone. The House of Wisdom produced an extraordinary constellation of mathematicians and scientists. There was Al-Kindi, often called the first philosopher of the Arab world, who worked on cryptography and frequency analysis. He essentially figured out that you could break substitution ciphers by analyzing how often different letters appear, which is a fundamentally mathematical insight. There was Thabit ibn Qurra, who translated and extended the works of Euclid and Archimedes, proved new theorems about amicable numbers, pairs of numbers where each is the sum of the proper divisors of the other, and developed early ideas about integration. There was Omar Khayyam, who you might know as a poet, the author of the Rubaiyat, but who was also a brilliant mathematician. In the late 11th century, Khayyam classified and solved cubic equations. That's equations involving x cubed, using the intersections of conic sections. He couldn't find algebraic formulas for the solutions the way we can for quadratics, but he showed that geometric methods could handle them systematically. He also worked on calendar reform, producing a solar calendar that was arguably more accurate than the Gregorian calendar we use today. And then there's the question of trigonometry, which the Islamic mathematicians essentially transformed from a tool of Greek astronomy into a discipline in its own right. The Greeks had worked with chords. If you draw a circle and then draw a straight line connecting 2 points on that circle, that's a chord. And Greek astronomers like Ptolemy had built elaborate tables of chord lengths for different angles. Indian mathematicians, particularly Aryabhata in the 5th century, shifted from chords to half chords, which is what we now call the sine function. Think about it. If you have a right triangle inscribed in a circle, the sine of an angle is the ratio of the opposite side to the hypotenuse, and geometrically that corresponds to half the chord of twice the angle. It's a more natural and useful function. Islamic mathematicians adopted the sine from Indian sources and then added the other trigonometric functions: cosine, tangent, cotangent, secant, cosecant, creating the full toolkit that you probably encountered in high school. Al-Battani, working in the late 9th and early 10th centuries, produced sine tables of remarkable accuracy and was among the first to use the tangent function systematically. These weren't abstract exercises. Trigonometry was essential for astronomy, for determining the direction of Mecca, for prayer, for navigation, for surveying land. The mathematics was driven by practical need, but it transcended those needs and became something universal. Here's what I find really beautiful about this period. The Islamic mathematical tradition wasn't just a bridge between Greek antiquity and the European Renaissance, though it's often described that way, and that framing does a disservice to the originality of what was accomplished. These were creative mathematicians pushing boundaries, asking new questions, developing new methods. Al-Haytham, known in Latin as Alhazen, working around the year 1000, essentially invented the scientific method in optics, using controlled experiments and mathematical analysis to understand how light and vision work. His book of optics influenced everyone from Roger Bacon to Kepler. He also worked on what's now called Alhazen's problem, finding the point on a curved mirror where light from one point reflects to another, which leads to a fourth-degree equation that he solved geometrically. Al-Samawal, in the 12th century, worked with what we'd now recognize as polynomial arithmetic and had ideas that anticipated aspects of mathematical induction. And Al-Kashi, working in Samarkand in the early 15th century, calculated pi to 16 decimal places, a record that would stand for nearly 2 centuries. 16 decimal places. Working by hand. The patience and precision that required is almost unimaginable. But eventually, the center of mathematical gravity shifted again. And this time, it shifted west, to Europe, where for centuries mathematics had been in a comparatively dormant state. The transmission happened gradually, through trade, through the Crusades, through the great translation centers in places like Toledo in Spain, where Arabic texts were translated into Latin. One of the key figures in this transmission was an Italian mathematician born around 1170 in Pisa. His name was Leonardo, though he's better known by his nickname, Fibonacci. His father was a merchant who worked in North Africa, and the young Leonardo traveled extensively in the Mediterranean world, learning from Arab and Indian mathematical traditions. In 1202, he published a book called Liber Abaci, the Book of Calculation, and this book was essentially a massive argument for why Europe should adopt the Hindu-Arabic numeral system instead of continuing to struggle with Roman numerals and counting boards. He demonstrated, through hundreds of practical problems involving commerce, currency conversion, and profit calculation, just how much more efficient the new system was. And buried in that book, almost as an afterthought, was a little problem about rabbits. How fast would a population of rabbits grow if each pair produced a new pair every month? The answer generates the sequence 1, 1, 2, 3, 5, 8, 13, 21, and so on, where each number is the sum of the two before it. The Fibonacci sequence. It shows up everywhere, in the spiral patterns of sunflower seeds, in the branching of trees, in the proportions of seashells. It's one of those places where mathematics and nature seem to speak the same language, and we'll come back to why that might be. But Fibonacci's most lasting contribution wasn't the sequence. It was convincing Europe to count properly. And once Europe had the right numerical tools, things started to accelerate. By the 15th and 16th centuries, Italian mathematicians were locked in fierce competitions to solve cubic and quartic equations, that's third and fourth degree polynomials. And these competitions were dramatic, public, high-stakes affairs. Imagine mathematical duels where your career and reputation hung on whether you could solve a set of problems faster than your rival. The story of how the cubic equation was finally cracked involves some of the most colorful characters in the history of mathematics. A stammering genius named Tartaglia, a gambling physician named Cardano, and a hot-tempered protege named Ferrari, and the tale of what happened between them is one of the juiciest in all of mathematics. So, let's get into it. It starts, really, with a professor named Scipione del Ferro, who taught at the University of Bologna in the early 1500s. Now, del Ferro was working on what was called the depressed cubic, a cubic equation where the squared term has been eliminated through a clever substitution. And sometime around 1515, maybe a little earlier, he figured out a general method for solving it. This was huge. For centuries, mathematicians had been able to solve linear equations, that's first degree, and quadratic equations, second degree. But the cubic had resisted every attempt, and del Ferro cracked it. But here's the thing. He didn't publish it. He kept it secret. And if that seems strange to you, you have to understand the world these Italian mathematicians lived in. University positions weren't secure the way we think of tenure today. Professors could be challenged to public mathematical duels, and if you lost, you could lose your job, your income, your reputation, everything. So having a secret weapon, a method nobody else knew, was like having an ace up your sleeve. Del Ferro held on to his solution for years, only sharing it on his deathbed with one of his students, a man named Antonio Maria Fior. Now, Fior was not a great mathematician. He was competent, but he wasn't brilliant. What he had, though, was del Ferro's secret formula. And in 1535, he made the mistake of challenging Niccolò Fontana to a public contest. Fontana is the man history remembers as Tartaglia, the stammerer. And the nickname came from a horrific childhood injury. When Tartaglia was about 12 years old, French soldiers sacked his hometown of Brescia in 1512, and a soldier slashed the boy across the face with a saber, cutting through his jaw and palate. He barely survived. He was left with a severe speech impediment for the rest of his life, and the cruel nickname stuck. But behind that stammer was one of the sharpest mathematical minds in Italy. So Fior challenged Tartaglia, and each man submitted 30 problems for the other to solve. Fior, confident in his secret weapon, submitted 30 cubic equations, all of the same type that del Ferro's method could handle. Tartaglia, on the other hand, submitted a diverse mix of problems. And here's what happened. In a burst of insight, just days before the deadline, Tartaglia independently figured out how to solve the cubic. Not just Del Ferro's particular type, but a broader class of cubics. He solved all 30 of Fior's problems in just 2 hours. Fior couldn't solve a single one of Tartaglia's. The victory was total, and it made Tartaglia famous. And this is where Girolamo Cardano enters the picture. Cardano was a physician, a gambler, an astrologer, a philosopher, and a mathematician. One of those Renaissance figures who seemed to do everything at once and do most of it brilliantly. He was also, by many accounts, not the most scrupulous person when it came to keeping promises. Cardano heard about Tartaglia's triumph and desperately wanted to know the method. He invited Tartaglia to Milan, flattered him, wined and dined him, and eventually persuaded Tartaglia to reveal the secret, but only under a solemn oath that Cardano would never publish it. Tartaglia shared the solution in the form of a poem, actually, a mnemonic verse that encoded the steps of the method. And Cardano, true to his word, didn't publish it, at least not right away. But then Cardano and his brilliant young student Lodovico Ferrari started working with the method, extending it, improving it. Ferrari, who was only about 18 at the time, managed to use the cubic solution as a stepping stone to solve the quartic, the fourth-degree equation. That's remarkable. This teenager cracked a problem that had stumped everyone for centuries, and he did it by reducing the quartic to a cubic and then applying Tartaglia's method. Now, Cardano had a dilemma. He had the cubic solution, the quartic solution, a whole beautiful framework of new mathematics, and he'd sworn not to publish any of it. But then he traveled to Bologna and got his hands on Del Ferro's original notes, which proved that Del Ferro had discovered the cubic solution before Tartaglia. Cardano used this as his justification. He argued that since Del Ferro had priority, the oath to Tartaglia didn't apply, and in 1545 he published everything in his masterwork, Ars Magna, the Great Art. It's one of the most important algebra books ever written. It contained the solutions to both the cubic and the quartic, and it pushed mathematics into territory that had been completely inaccessible before. Tartaglia was furious. He felt utterly betrayed, and honestly, you can understand why. He'd shared his discovery in confidence, under oath, and now it was published under someone else's name. He attacked Cardano publicly, but it was Ferrari who stepped up to defend his mentor, challenging Tartaglia to a public debate. Ferrari was young, aggressive, and brilliant. Tartaglia was reluctant. He wanted to face Cardano, not some student, but eventually he accepted. The debate took place in Milan in 1548, and by most accounts, Ferrari won decisively. Tartaglia's reputation never fully recovered, and he died in relative obscurity. Ferrari, meanwhile, went on to a prestigious career, though he died young, possibly poisoned by his own sister, if you can believe that. And Cardano's later life was marked by tragedy too. His eldest son was executed for poisoning his wife, and Cardano himself was arrested by the Inquisition for casting the horoscope of Jesus Christ. He spent his final years in Rome, living on a papal pension, writing his autobiography. The whole saga reads more like a Renaissance drama than a chapter in mathematics. But here's what matters beyond the drama. The Ars Magna didn't just solve specific equations. It forced mathematicians to confront something deeply unsettling. When you apply Cardano's formula to certain cubic equations, equations that clearly have real solutions you can verify, the intermediate steps of the calculation require you to take the square root of negative numbers. Think about that. You need to work with a number that, when multiplied by itself, gives you a negative result. No ordinary number does that. A positive times a positive is positive. A negative times a negative is also positive. There's no real number whose square is negative. And yet, if you just held your nose and pushed through the calculation, treating these impossible square roots as if they were legitimate, you'd get the right answer at the end. The weird square roots would cancel out, and you'd be left with a perfectly normal, real solution. This was deeply uncomfortable. Raffaele Bombelli, an Italian engineer working a few decades after Cardano, was the first to really grapple with this head-on. Around 1572, in his own algebra textbook, Bombelli laid out explicit rules for calculating with these strange quantities, what he called plus of minus and minus of minus. He showed that you could add them, multiply them, and manipulate them consistently. He didn't fully understand what they were, but he demonstrated that they worked. And this was the birth of what we now call imaginary numbers and complex numbers, though those names wouldn't come for another century or so. Descartes would dismissively call them imaginary in the 1600s, and the name stuck, which is unfortunate, because it makes people think they're somehow fake or made up. They're not. They're just as real numbers, in the sense that they follow consistent rules and they describe real phenomena. Today, complex numbers are absolutely essential in electrical engineering, quantum mechanics, signal processing, fluid dynamics, you name it. Every time you use a cell phone, the mathematics handling the signal involves complex numbers, and it all traces back to Cardano's formula spitting out square roots of negative numbers and Bombelli refusing to look away. Now, while we're in the 16th century, there's another revolution happening that's going to change mathematics just as profoundly, and it comes from an unexpected direction. It comes from astronomy, specifically from the problem of multiplying very large numbers. If you're an astronomer in the late 1500s, someone like Tycho Brahe, meticulously recording the positions of stars and planets, you spend an enormous amount of your time doing tedious multiplication and division of numbers with many digits. It's slow, it's error-prone, and it's exhausting. Mistakes in calculation could set your work back by weeks. And a Scottish landowner named John Napier, sitting in his castle near Edinburgh, decided to do something about it. Napier was a fascinating character, part mathematician, part theologian, part inventor of military weapons. His neighbors suspected him of being a sorcerer because he walked around with a black rooster that he claimed could detect liars among his servants. But his mathematical mind was extraordinary, and he spent 20 years, developing a tool that would transform calculation forever. What he invented and published in 1614 was logarithms. And the core idea is so elegant, it's worth savoring for a moment. Think about what happens when you add exponents. If you have 10 to the second power, that's 100, and you multiply it by 10 to the third power, that's 1,000. You get 10 to the fifth power, which is 100,000. You multiplied the numbers, but you added the exponents. 2 plus 3 equals 5. What Napier realized was that you could exploit this relationship to turn any multiplication problem into an addition problem. If you could express any number as a power of some base, then instead of multiplying those numbers directly, you could just look up their exponents in a table, add the exponents together, and then look up the result. Multiplication reduced to addition. Division reduced to subtraction. For astronomers and navigators who spent their lives multiplying 6-digit numbers by hand, this was like being handed a calculator. The French mathematician Laplace would later say that logarithms, by halving the labor of calculation, doubled the life of the astronomer. Henry Briggs, a professor at Gresham College in London, was so excited by Napier's work that he traveled all the way to Edinburgh to meet him. Together, they refined the system into common logarithms, base 10, and Briggs spent years computing detailed logarithmic tables by hand. These tables became indispensable tools for scientists, engineers, and navigators for the next 350 years. If you've ever seen a slide rule, that elegant analog computing device that engineers carried in their pockets well into the 1970s, that's a physical embodiment of logarithms. Two sliding scales where addition of lengths corresponds to multiplication of numbers. Every engineer who designed a bridge, an airplane, or a skyscraper before the pocket calculator era did their calculations with logarithms and slide rules. And the concept goes even deeper than practical computation. Logarithmic scales turn out to describe how we actually perceive the world. The decibel scale for sound, the Richter scale for earthquakes, the pH scale for acidity, all logarithmic, because our senses respond to proportional changes rather than absolute ones. But Napier and logarithms are really part of a larger story about the relationship between algebra and geometry, a relationship that was about to be completely reimagined by a French philosopher lying in bed one morning, watching a fly crawl across his ceiling, and having an idea that would change everything. René Descartes, lying there in that warm bed. Because Descartes loved sleeping in, he was famous for it. He rarely got up before 11 in the morning, watching that fly move along the ceiling, and realizing something so simple and so profound that it's hard to believe nobody had thought of it before. The fly was at a specific point on the ceiling, and you could describe that point with two numbers: how far along the ceiling it was from one wall and how far from the adjacent wall. Two numbers. That's all you needed. Any point on any flat surface could be pinned down with just a pair of numbers. Now, this might sound obvious to you because you grew up with it. Every graph you ever drew in school, every map coordinate you ever typed into your phone, every pixel on the screen you're not looking at right now because your eyes are probably closed, they all use this idea. But in 1637, when Descartes published his method, it was revolutionary because it did something nobody had done before. It married algebra and geometry into a single unified language. Before Descartes, algebra was about equations, symbols, unknowns, relationships between quantities. And geometry was about shapes, lines, circles, curves drawn with compass and straight edge, the kind of thing Euclid would have recognized. They were separate kingdoms. Descartes built a bridge between them. Here's how it works, and it's beautifully simple. You draw two perpendicular lines, one horizontal, one vertical, and you call them axes. Every point in the plane gets a pair of numbers, an x-coordinate and a y-coordinate. And now, here's the magic. A geometric shape becomes an equation, and an equation becomes a geometric shape. A circle isn't just a round thing you draw with a compass anymore. It's x squared plus y squared equals r squared. A straight line is y equals mx plus b. A parabola, an ellipse, a hyperbola. Every curve the Greeks had studied purely through geometry. Descartes could now describe purely through algebra, and that means you could use algebraic techniques to answer geometric questions, and geometric intuition to understand algebraic problems. The two fields, which had been developing in parallel for 2,000 years, suddenly became one. This is coordinate geometry, or analytic geometry, and it's one of those ideas that, once you have it, you can't imagine doing mathematics without it. Think about what it unlocked. You want to find where two curves intersect? set their equations equal, and solve. You want to know the slope of a curve at a specific point. That's a question you can now phrase algebraically. And that question, that exact question about slopes of curves, is going to lead directly to calculus. But we'll get there. Descartes published this in an appendix to a philosophical work called Discourse on the Method, the same work that contains his famous "I think, therefore I am." The mathematics was almost an afterthought, tucked into the back, and yet it became arguably the most consequential part of the entire book. And Descartes, being Descartes, he deliberately left out steps in his proofs, saying he wanted the reader to have the pleasure of discovering things for themselves, which drove other mathematicians absolutely crazy. But that was Descartes, brilliant, arrogant, and not particularly interested in making things easy for anyone else. Now, around the same time, another Frenchman was doing mathematics that was equally extraordinary, but in a completely different way. Pierre de Fermat. We've already met him, haven't we? Scribbling that maddening note about his last theorem in the margin of Diophantus. But Fermat was doing so much more than that. He independently developed a version of coordinate geometry around the same time as Descartes, though he shared his work through letters rather than publishing formally. He also developed methods for finding maxima and minima of curves, the highest and lowest points, using techniques that were essentially pre-calculus. Fermat would look at a curve, imagine nudging a point slightly along it, and see what happened to the value. When the value stopped changing, when a tiny nudge made essentially no difference, you were at a peak or a valley. This is stunningly close to what we now call taking a derivative and setting it equal to zero. Fermat was dancing right at the edge of calculus, decades before Newton and Leibniz. And Fermat was doing all of this as an amateur. By day, he was a lawyer and magistrate in Toulouse. Mathematics was his hobby, his evening passion. He'd work through problems after dinner and send his results to friends and correspondents, often without proofs, often as challenges. Can you prove this? Can you solve that? He was, in many ways, the greatest amateur mathematician who ever lived, and his contributions to number theory alone would have secured his place in history, even without the famous last theorem. But let's talk about what was building toward the biggest mathematical revolution since the Greeks invented proof. By the mid-1600s, mathematicians across Europe were circling around a cluster of related problems that all seemed to require similar techniques. How do you find the area under a curve? How do you find the slope of a curve at a point? How do you find the length of a curved line? How do you describe motion that's accelerating or decelerating? These problems came from everywhere, from physics, from astronomy, from engineering, from pure geometric curiosity, and they all pointed towards something that didn't quite exist yet. Archimedes had gotten tantalizingly close with his method of exhaustion, remember? Slicing areas into thinner and thinner strips, getting better and better approximations. Cavalieri in Italy formalized something similar in the 1630s with his method of indivisibles, imagining a shape as being made up of infinitely many, infinitely thin slices. Wallace in England was computing areas under curves using clever algebraic tricks. Barrow, Newton's teacher at Cambridge, was exploring the relationship between tangent problems and area problems. The pieces were all there, scattered across different minds in different countries. What was needed was someone to see the whole picture, to realize that all these problems were really one problem, and to build a systematic method for solving them. Two people did this, essentially simultaneously, and the result was one of the most bitter priority disputes in the history of science. Isaac Newton, in the autumn of 1665, was a 22-year-old student at Cambridge when the university closed because of the plague. He went home to his family's farm in Woolsthorpe, Lincolnshire, and over the next 18 months, the famous Annus Mirabilis, the miracle year, though it was really closer to 2 years, he developed his method of fluxions. What Newton realized was that the problem of finding tangent lines to curves and the problem of finding areas under curves were inverse operations. They were the same thing, run in opposite directions. If you have a curve and you find its rate of change at every point, its slope, its fluxion, you get a new function. And if you take that new function and find the area under it, you get back to the original curve. Differentiation and integration are inverses of each other. This is the fundamental theorem of calculus, and it is, without exaggeration, one of the most important insights in the history of human thought. Think about what that means practically. Before this, finding areas under curves was a separate, ad hoc puzzle every time. You'd have to be as clever as Archimedes, inventing a new trick for each new shape. But now there was a machine, a systematic procedure. If you could differentiate a function, which followed rules, learnable rules, you could integrate it, and vice versa. Calculus turned an art into a science. Newton, though, was pathologically secretive. He didn't publish. He sat on his results for years, decades even, sharing them only with a small circle of correspondents. Meanwhile, Gottfried Wilhelm Leibniz, a German polymath, philosopher, diplomat, logician, inventor, independently developed his own version of calculus in the mid-1670s, and he published it in 1684 and 1686. Leibniz's notation was different from Newton's, and frankly, it was better. The dx and dy notation, the integral sign that looks like an elongated S for summa, that's all Leibniz, and it's what we still use today because it's so expressive and flexible. Newton's dot notation, putting a dot over a variable to indicate its rate of change, survives mainly in physics, but Leibniz's notation won the war. And it was a war. When Leibniz published, Newton's allies accused him of plagiarism, of having seen Newton's unpublished manuscripts during a visit to London and stealing the ideas. Leibniz's allies fired back that Newton was the one trying to claim credit after the fact. The Royal Society in London conducted an investigation, but Newton was president of the Royal Society at the time, and he essentially wrote the report himself, which unsurprisingly concluded that Newton had priority. The dispute poisoned relations between English and continental mathematicians for a century. English mathematicians, loyal to Newton, stubbornly stuck with his inferior notation and fell behind their European counterparts, who adopted Leibniz's more powerful symbolic framework and raced ahead. The historical consensus today is that both men developed calculus independently. They were drawing on the same body of prior work, Fermat, Cavalieri, Barrow, Wallis, and they arrived at the same destination by somewhat different paths. Newton's approach was more physical and geometric, rooted in his thinking about motion and forces. Leibniz's was more algebraic and symbolic, rooted in his passion for formal logic and universal languages. Both were extraordinary achievements, and the tragedy is that the priority dispute overshadowed the mathematics itself. But here's what matters for our story. Calculus changed everything. And I mean everything. Suddenly, you could describe a world in motion. Newton used his calculus to formulate the laws of motion and universal gravitation, publishing them in the Principia in 1687. Arguably the most important scientific book ever written. The motion of planets, the trajectories of cannonballs, the tides, the shape of the earth, all of it fell out of a handful of equations that you could only write down and solve because calculus existed. Engineering, which had been largely empirical, build it, see if it stands, could now become analytical. You could calculate the stresses in a beam, the flow of water through a pipe, the orbit of a satellite, because you had the mathematical language to describe continuous change. And the Bernoulli family. There's a story worth telling. The Bernoullis were a Swiss family that produced something like 8 prominent mathematicians across 3 generations, which is statistically absurd. Jakob and Johann Bernoulli were among the first to fully absorb Leibniz's calculus and push it further. Johann was brilliant and also viciously competitive. He competed with his own brother. He competed with his own son Daniel. He once tried to pass off Daniel's work as his own. Daniel Bernoulli, despite his father's jealousy, went on to develop the principle that bears his name, Bernoulli's principle, the one that helps explain how airplane wings generate lift, how a carburetor mixes fuel and air, why a shower curtain gets sucked inward when you turn on the water. All flowing from calculus, all made possible because someone figured out how to talk about rates of change. And then there was Leonhard Euler, who studied under Johann Bernoulli and became arguably the most prolific mathematician in history. Euler published over 800 papers and books. He contributed to virtually every branch of mathematics that existed in his time and invented several new ones. He standardized much of the notation we use today, the function notation f of x, the number e for the base of natural logarithms, the Greek letter pi for the ratio of circumference to diameter, the letter I for the square root of -1. Remember Bombelli wrestling with those strange square roots of negatives back in the 1570s? Euler took those imaginary numbers and showed they were anything but imaginary. He discovered what's often called the most beautiful equation in mathematics. E to the power of I times pi plus 1 equals 0. 5 fundamental constants, ei, pi, 1, and 0, linked in a single elegant identity. It's the kind of thing that makes mathematicians feel something close to awe, a sense that mathematics isn't just a tool humans invented, but something woven into the fabric of reality itself, waiting to be uncovered. Euler didn't just collect results, though. He had this extraordinary ability to see connections between things that nobody else realized were related. He linked number theory to analysis, geometry to algebra, the continuous to the discrete. And he did all of this while going blind. By his late 50s, Euler had lost sight in both eyes, and his productivity actually increased. He could hold enormous calculations in his head, dictating papers to assistants, working from memory with a fluency that astonished everyone around him. When he died in 1783, he left behind such a mountain of unpublished work that the St. Petersburg Academy kept publishing his papers for nearly 50 more years after his death. Think about that. Half a century of posthumous publications. But even as Euler was reshaping mathematics from his study in St. Petersburg, the world was changing around him. The 18th century was the age of enlightenment, of revolution, of industry beginning to stir. And mathematics was about to enter a period that would challenge its very foundations, not just extending what was known, but questioning whether the tools mathematicians had been using for a century actually made sense at all. Here's the thing. Calculus worked. Newton used it to predict planetary orbits with stunning accuracy. Euler used it to solve problems in fluid dynamics, mechanics, optics, you name it. Engineers were beginning to rely on it. But if you looked closely at the logical foundations of calculus, they were, to put it politely, a mess. Newton talked about quantities that were vanishingly small, but not zero. His fluxions depended on these infinitesimals that appeared and disappeared as needed. Leibniz was no better, using infinitely small differentials in ways that gave correct answers, but couldn't really be justified rigorously. The philosopher George Berkeley famously mocked these infinitesimals in 1734, calling them ghosts of departed quantities. And he had a point. Mathematicians were dividing by things that were supposedly zero, but also not zero, depending on which step of the calculation they were in. It was logically incoherent, and everybody kind of knew it, but the results were so powerful and so useful that people mostly just shrugged and kept going. That couldn't last forever. In the early 19th century, a French mathematician named Augustin Louis Cauchy began the hard work of putting calculus on solid ground. Cauchy was a fascinating figure, devoutly Catholic, politically conservative, enormously productive, and not always easy to get along with. He introduced the rigorous definition of a limit, replacing those ghostly infinitesimals with precise language about what it means for a sequence or function to approach a value. Instead of saying a quantity becomes infinitely small, Cauchy said, "For any degree of closeness you specify, no matter how tiny, I can show you a point beyond which the function stays that close to the limit. It's a subtle shift, but it changes everything. You're no longer talking about infinitely small quantities as actual things. You're talking about a process, a relationship between precision and proximity. And that's something you can reason about logically without contradiction." Cauchy's work was continued and refined by Karl Weierstrass, a German mathematician who spent years as a secondary school teacher before his genius was recognized. Weierstrass gave us the epsilon-delta definition of limits that every calculus student still encounters today. If you've ever taken a rigorous calculus course and been baffled by all those epsilons and deltas, that's Weierstrass. He was obsessive about precision, about eliminating every last appeal to intuition or hand-waving, and in the process, he discovered something unsettling: functions that were continuous everywhere but differentiable nowhere. Imagine a curve with no breaks or jumps, perfectly connected, but so jagged at every single point that you can never draw a tangent line to it. It's like a coastline that's rough at every scale, no matter how much you zoom in. These pathological functions horrified many mathematicians. They seemed monstrous, unnatural. But they were logically valid, and their existence proved that intuition alone was not a reliable guide in mathematics. You needed rigor. You needed proof. Now, while Cauchy and Weierstrass were shoring up the foundations of calculus, something even more revolutionary was happening in geometry. Remember Euclid's parallel postulate, that fifth axiom that felt different from the others, the one that said, through a point, not on a line. There's exactly one parallel line. For over 2,000 years, mathematicians had tried to prove it from the other four axioms, convinced it was a theorem in disguise rather than a true axiom. Every attempt failed. And in the early 19th century, 3 mathematicians independently realized why. Because it wasn't provable. You could replace it with a different assumption and get a perfectly consistent, perfectly logical geometry that simply wasn't Euclidean. Carl Friedrich Gauss, often called the Prince of Mathematicians, appears to have understood this first, but never published, possibly because he feared the controversy. Gauss was cautious by nature, a perfectionist who withheld results until they met his exacting standards. His personal motto was, few but ripe. But János Bolyai, a young Hungarian officer, and Nikolai Lobachevsky, a Russian professor in Kazan, independently published their discoveries of non-Euclidean geometry in the late 1820s and early 1830s. Bolyai's father, himself a mathematician and friend of Gauss, had begged his son not to pursue the parallel postulate. "For God's sake, leave the parallel postulate alone," he wrote, knowing how many careers it had consumed. But Janos couldn't let it go, and what he found was extraordinary. By assuming that through a point not on a line, there are multiple parallel lines, he constructed a geometry that was internally consistent, logically airtight, and completely different from anything Euclid described. Lobachevsky arrived at essentially the same geometry independently, working in isolation in Russia. Think about what this means. For 2 millennia, Euclidean geometry wasn't just mathematics. It was truth. It was how space worked. Kant had argued that Euclidean geometry was a necessary feature of human perception, built into the very structure of how we experience the world. And now these mathematicians were saying, actually, there are other geometries, equally valid, equally consistent. Euclid's is one option among many. The universe might be Euclidean, or it might not. That's an empirical question, not a mathematical one. And here's the kicker. It turned out the universe isn't Euclidean. But that realization would come later, with Einstein, and we'll get there. For now, the important thing is what non-Euclidean geometry did to mathematics itself. It forced mathematicians to reckon with the idea that their subject wasn't about describing physical reality directly. It was about exploring the consequences of axioms, whatever those axioms might be. Mathematics was becoming more abstract, more self-aware, more concerned with its own internal structure than with the world outside. This shift toward abstraction accelerated through the 19th century. In algebra, a young Frenchman named Évariste Galois took it to an entirely new level, and his story is one of the most dramatic in all of mathematics. Galois was born in 1811, showed extraordinary mathematical talent as a teenager, and was dead by 20. He was killed in a duel in 1832. The exact circumstances are still debated, but it likely involved a romantic entanglement, possibly political intrigue, possibly both. The night before the duel, knowing he might die, Galois frantically wrote down his mathematical ideas in a letter to a friend, scribbling in the margins, "I have no time," as he raced to capture everything in his head. Those hastily written pages contained the seeds of what we now call group theory, a framework so powerful and so general that it would eventually unify vast stretches of mathematics and become essential to modern physics. What Galois was trying to solve was a specific problem. Why is there no general formula for solving polynomial equations of degree 5 or higher? Remember the cubic formula that Cardano published, and Ferrari's quartic formula? Mathematicians had naturally tried to find a quintic formula, a general solution for fifth-degree equations, and they couldn't. In 1799, Paolo Ruffini had given an incomplete proof that no such formula exists, and in 1824, the Norwegian mathematician Niels Henrik Abel, another tragically short-lived genius, dead of tuberculosis at 26, gave a rigorous proof. But Galois went further. He didn't just prove that the quintic was unsolvable by radicals. He developed a complete theory explaining exactly which equations could be solved and which couldn't, based on the symmetry properties of their roots. The concept of symmetry here is key. Galois looked at the ways you could permute the roots of an equation, swap them around, without changing the fundamental relationships between them. These permutations form a mathematical structure called a group, and the properties of that group determine whether the equation is solvable. It's an incredibly deep insight. Instead of looking at the equation itself, you look at its symmetries. And this idea that the important thing isn't the object itself but its symmetries would turn out to be one of the most fertile ideas in all of modern science. When physicists in the 20th century developed the standard model of particle physics, group theory was the language they used. The fundamental forces of nature, electromagnetism, the weak force, the strong force, are described by symmetry groups. Galois, scribbling by candlelight before a duel that would kill him, was building tools that would help explain the universe at its most fundamental level. Meanwhile, another kind of revolution was brewing, one that would connect mathematics to the practical world in ways nobody anticipated. In 1854, George Boole, a self-taught English mathematician who never attended university, published a work called An Investigation of the Laws of Thought. Boole created an algebra of logic, a system where logical propositions could be manipulated using mathematical operations. True and false became 1 and 0. Logical and became multiplication. Logical OR became addition. It was elegant, it was strange, and for decades it seemed like a curiosity, a clever parlor trick with no practical application. But 80 years later, a young MIT graduate student named Claude Shannon realized that Boole's algebra perfectly described the behavior of electrical switching circuits. Every switch is either open or closed, 1 or 0. Connect switches in series and you get AND. Connect them in parallel and you get OR. Shannon's 1937 master's thesis, often called the most important master's thesis of the 20th century, laid the theoretical foundation for digital circuit design. Every computer, every smartphone, every piece of digital technology you've ever touched operates on Boolean algebra. Boole, working in the 1850s, had no idea he was writing the mathematical language of the information age. He thought he was studying the laws of human thought. Instead, he gave us the laws of machine thought. And this is something that happens again and again in the history of mathematics. Ideas developed in pure abstraction, with no practical purpose in mind, turn out to be exactly what's needed decades or centuries later when technology catches up. The mathematicians of the 19th century were building an enormous warehouse of abstract tools, and the 20th century would raid that warehouse relentlessly. But before we get to the 20th century, there's one more 19th century figure we need to talk about. Someone whose work would shake mathematics to its core and provoke a crisis that would reshape how mathematicians understood the very foundations of their discipline. His name was Georg Cantor, and what he discovered, or perhaps revealed, was that infinity itself was far stranger than anyone had imagined. Cantor was born in St. Petersburg in 1845, though his family moved to Germany when he was young, and it was in the German mathematical tradition that he would spend his career. He ended up at the University of Halle, which was not one of the prestigious centers of mathematics, not Berlin, not Göttingen. And that geographic marginality would matter, because when Cantor began publishing his most radical ideas in the 1870s and 1880s, the mathematical establishment's resistance would be led by powerful figures at those elite institutions, and Cantor, stuck at Halle, lacked the institutional weight to fight back on equal footing. Here's what Cantor did. He asked a question that sounds almost childishly simple. Are all infinities the same size? Think about that for a moment. You've got the counting numbers, 1, 2, 3, 4, going on forever. And you've got the even numbers, 2, 4, 6, 8, also going on forever. Intuitively, you might say there are fewer even numbers, right? After all, the even numbers are a subset of the counting numbers. You're skipping every other one. But Cantor showed that you can pair them up perfectly. 1 goes with 2, 2 goes with 4, 3 goes with 6, 4 goes with 8. And every counting number gets matched to exactly one even number, and every even number gets matched to exactly one counting number. No leftovers on either side. In a precise mathematical sense, there are exactly as many even numbers as counting numbers. They're the same size of infinity. He called this size Aleph null, the smallest infinity. Now you might think this is just a quirk. Maybe all infinite sets are the same size, and infinity is infinity is infinity. But here's where Cantor dropped the bombshell. In 1874, he proved that the real numbers, all the points on the number line, including all those irrational numbers with their infinite non-repeating decimals, cannot be put into a one-to-one correspondence with the counting numbers. There are strictly more real numbers than counting numbers. The infinity of the real numbers is bigger than the infinity of the whole numbers. His proof is beautiful, and it's worth walking through because it's one of those arguments that, once you see it, changes how you think. It's called the diagonal argument, and the version he published in 1891 goes something like this. Suppose someone claims they've made a complete list of all real numbers between 0 and 1, written out as infinite decimals. The first number on the list has some digit in the first decimal place, some digit in the second, and so on. The second number has its own string of digits. Now, Cantor says, I'll build a new number that's definitely not on your list. For the first digit of my new number, I look at the first digit of the first number on your list, and I pick something different. For the second digit, I look at the second digit of the second number and pick something different. For the third digit, I look at the third digit of the third number and pick something different. I go diagonally down the list. The number I construct differs from the first number in at least the first decimal place, from the second number in at least the second decimal place, from every number on the list in at least one place. So my new number can't be on the list. But I can do this no matter what list you give me. Therefore, no list can contain all the real numbers. They're uncountable. They represent a fundamentally larger infinity. And Cantor didn't stop there. He showed that you can always build a larger infinity from any given infinity by considering the set of all subsets, the power set. So there's not just one bigger infinity. There's an infinite hierarchy of infinities, each one unimaginably larger than the last. Infinity wasn't a single concept anymore. It was a landscape, a vast architecture of different sizes stretching upward without end. This was, to put it mildly, controversial. Leopold Kronecker, one of the most powerful mathematicians in Berlin, was openly hostile. Kronecker believed mathematics should be built on the whole numbers and finite constructions. He reportedly called Cantor a corrupter of youth and worked to block his publications and his career advancement. Henri Poincaré, the great French mathematician, called Cantor's set theory a disease from which mathematics would eventually recover. The resistance wasn't just intellectual, it was personal, and it was vicious. Cantor suffered repeated bouts of depression throughout his life, spending time in sanatoriums. It's impossible to say exactly how much the professional hostility contributed to his mental illness, but it certainly didn't help. He died in 1918 in a sanatorium in Halle, largely impoverished. But here's the thing. Cantor was right, and the mathematics community came to recognize it even during his lifetime. David Hilbert, who would become arguably the most influential mathematician of the early 20th century, declared that no one would expel mathematicians from the paradise that Cantor had created. Set theory became the foundation of modern mathematics. Virtually every branch of mathematics today is built on set theoretic foundations. When mathematicians define numbers, functions, spaces, structures, they define them in terms of sets, and yet Cantor's work also opened a wound that wouldn't heal easily. Within set theory itself, paradoxes emerged. Bertrand Russell, in 1901, discovered the most famous one. Consider the set of all sets that do not contain themselves. Does it contain itself? If it does, then by definition it shouldn't. If it doesn't, then by definition it should. It's a contradiction either way. Russell's paradox showed that naive set theory, the intuitive version where you can define any set you like, was inconsistent. It could generate contradictions. And contradictions in mathematics are fatal, because from a contradiction, you can prove literally anything. This kicked off what's sometimes called the foundational crisis of mathematics, and it consumed some of the greatest minds of the early 20th century. How do you put mathematics on a solid foundation? How do you make sure the basic rules of the game don't lead to contradictions? Several camps emerged. The logicists, led by Russell and Alfred North Whitehead, tried to reduce all of mathematics to pure logic. Their monumental work, Principia Mathematica, published in 3 volumes between 1910 and 1913, attempted to build mathematics from the ground up using only logical axioms. It famously takes hundreds of pages before they can prove that 1 + 1 = 2. It's an extraordinary intellectual achievement, but it's also extraordinarily unwieldy, and it didn't fully succeed in its ambitions. The formalists, led by Hilbert, took a different approach. Hilbert wanted to treat mathematics as a formal game played with symbols according to precise rules. The symbols don't need to mean anything. What matters is that the rules are consistent, that they can never produce a contradiction. Hilbert laid out a famous program: prove, using only simple and uncontroversial methods, that the formal systems of mathematics are consistent. If you could do that, you'd know the foundations were solid, and mathematicians could go about their work with confidence. And then there were the intuitionists, led by the Dutch mathematician L.E.J. Brouwer, who took the most radical position of all. Brouwer argued that mathematics is a human mental construction, and that a mathematical object exists only if you can explicitly construct it. He rejected the law of the excluded middle, the principle that every statement is either true or false, when applied to infinite sets. For Brouwer, you couldn't just prove that something exists by showing that its non-existence leads to a contradiction. You had to actually build it, exhibit it, show it to the world. This meant throwing out large portions of classical mathematics, which most mathematicians found unacceptable. So you had this incredible intellectual battle raging in the 1920s, with the very meaning of mathematics at stake. And then, in 1931, a quiet, meticulous young Austrian logician named Kurt Gödel published a paper that changed everything. Gödel was 25 years old, working in Vienna, and his incompleteness theorems are among the most profound results in the entire history of human thought. Here's what Gödel proved, and I want you to really sit with this because it's remarkable. His first incompleteness theorem says that in any consistent formal system that's powerful enough to describe basic arithmetic, there are true statements that cannot be proved within that system. Not statements we haven't proved yet. Statements that can never be proved in principle using the rules of that system. Mathematics, if it's consistent, is necessarily incomplete. There will always be truths beyond the reach of proof. His second incompleteness theorem is even more devastating for Hilbert's program. It says that such a system cannot prove its own consistency. You can't use mathematics to prove that mathematics is free of contradictions. At least, not without stepping outside the system and using stronger assumptions that themselves need justification. Hilbert's dream of a complete, self-verifying foundation for mathematics was impossible. Not just difficult, logically impossible. Gödel's proofs are technically intricate, involving a brilliant trick where he encoded logical statements as numbers so that a formal system could effectively talk about itself. But the philosophical implications are what echo through the decades. Mathematics is not a closed, self-contained system where every truth can be captured by a fixed set of rules. It's open-ended, inexhaustible. There's always more to discover, and there are always truths that lie just beyond the reach of any particular framework. Now, you might think this threw mathematics into chaos, but in practice, working mathematicians mostly shrugged and kept going. Gödel's theorems tell you about the limits of formal systems in the abstract, but they don't prevent you from proving specific theorems about specific problems. Day-to-day mathematics continued to flourish throughout the 20th century, branching into dozens of specialties, producing results of breathtaking beauty and power. And this is where we could spend years, literally years, talking about what happened next. The 20th century was an explosion. Topology, abstract algebra, functional analysis, algebraic geometry, number theory, combinatorics, probability theory, dynamical systems. Each of these became vast fields with their own communities, their own journals, their own conferences. Mathematics grew so large that by mid-century, no single person could claim to understand all of it. That era of the universal mathematician, the Euler who could contribute to every branch, was gone. But let me pull out just a few threads to give you a sense of where things went, because some of them connect beautifully to stories we've already told. Remember Euclid's parallel postulate, and how Gauss and Bolyai and Lobachevsky showed that you could build perfectly consistent geometries without it? That story found its ultimate payoff in 1915 when Albert Einstein published his general theory of relativity. Einstein needed a mathematical framework for describing curved spacetime, a universe where space itself bends and warps in the presence of mass and energy. And the mathematics he needed was Riemannian geometry, developed by Bernhard Riemann in the 1850s as a generalization of those non-Euclidean ideas. Riemann had built the tools decades before anyone knew what they'd be used for. When Einstein went looking for the right mathematical language, it was sitting there, waiting for him. Pure mathematics, developed for its own sake, turned out to describe the actual geometry of the universe. Or think about the group theory that Galois sketched out the night before his fatal duel. By the 20th century, group theory had become the language of symmetry in physics. The standard model of particle physics, our best description of the fundamental forces in particles, is built on symmetry groups. The reason physicists predicted the existence of certain particles before they were ever observed in experiments is that the mathematical structure demanded them. The symmetry groups had slots that needed filling. Galois, scribbling in candlelight in 1832, could never have imagined quarks and gluons, but the abstract structures he discovered are the same ones holding the modern picture of reality together. And then there's Alan Turing, who in 1936, partly inspired by Gödel's work, formalized the concept of computation itself. Turing imagined an abstract machine, absurdly simple, just a tape and a read-write head following rules, and showed that this simple machine could compute anything that's computable. His work, alongside that of Alonzo Church, defined the very boundaries of what algorithms can and cannot do. And within a decade, actual physical computers were being built, and the abstract theory of computation became the most practically transformative branch of mathematics in human history. So here we are. And if you've been drifting in and out through all of this, that's perfectly fine. Let me just leave you with this thought as you settle deeper into wherever you are right now. Mathematics is the oldest continuous intellectual project in human history. It stretches from those tally marks on the Ashango bone, 30,000 years old, carved by someone whose name we'll never know, all the way to theorems being proved tonight by someone hunched over a laptop or scribbling on a whiteboard in a university building with the lights still on at 2 a.m. And the remarkable thing, the truly astonishing thing, is that it's all connected. The geometry Euclid formalized describes the same spatial relationships that Sumerian surveyors measured in muddy fields. The algebra al-Khwarizmi systematized grew into the abstract structures Galois died for. The logic Boole played with became the circuitry in the device you might be listening to right now. The infinities Cantor mapped, the limits Cauchy and Weierstrass pinned down, the incompleteness Gödel revealed, they're all part of one enormous, sprawling, unfinished story. And it is unfinished. That's maybe the most beautiful part. There are major open problems right now: the Riemann hypothesis, the P versus NP problem, the Navier-Stokes equations, that the greatest mathematical minds alive are working on, and nobody knows when or if they'll be solved. Mathematics isn't a museum of completed achievements. It's a living, growing thing, and the frontier is as wild and uncertain today as it was when Pythagoras first realized that the square root of 2 couldn't be written as a fraction. So let that thought carry you wherever you're going. Thousands of years of human beings staring at patterns, asking why, pushing a little further into the unknown. And tomorrow, someone will push a little further still. But for now, that's enough. Let the numbers and the names and the stories settle around you like a blanket, and rest